Fundamental theorem of calculus. I tell my kids this is a big day in your life. Write down January 12th, the day you learned fundamental theorem of calculus. Nobody's excited? Okay, so some people say this is like the most important discovery in the history of mathematics. Yeah. Okay. No. That's what my kids said, the same thing. And they were like, wouldn't that be when we learned to multiply? No. Okay, it's all leading up to this, guys. It's all about this. Okay, so fundamental theorem. I could just give you the formula and say, hey, here's the formula. You're going to memorize it. You're going to use it all the time. Okay, but I kind of want to develop it for you so that it makes sense. Okay? All right, so we're going to start off with a silly example. We have a ladybug. Walks along a straight path, it's very convenient, at a constant rate of 3 feet per minute. My daughter really likes ladybugs. She likes to go around and collect them and put them in like these jars, and then she forgets about them.
Do they live?
No. Okay, so how far has a ladybug walked in 4 minutes? How did you do that so fast? Hold on, don't we need to like draw a picture? Oh. Don't I need to see like, all right, here's my velocity, and we've got 4 feet per second, right? Feet per second. And I'm accumulating the change that takes place over this 3-minute time interval. So is that what you did? You thought about this graphically, and is that what you did? Okay. You didn't use calculus? Why did we not need calculus for this problem? Constant, okay? It's constant. Did we need, right, 4 feet per second times 3 seconds. I didn't really need a graph, right? So 3 times 4, this ladybug walks 3 feet the first minute, 3 feet the second minute, and so on. So 12 feet. Good? How fast is the ladybug traveling at 1.234 minutes? 3 feet per minute. How did you know? Constant, right? Doesn't change. All right, so like I said, my daughter likes to collect ladybugs, so I want to go pick up this ladybug. Where is it after 2 minutes?
0 minutes?
Wait, what?
You pick it up at 0 minutes?
No, I want to go find it. Like, I want to find it. Where is it after 2 minutes? But where is it?
6 feet along.
But I want to go get it, so where is it? Where's this ladybug? Do I? From what? Can you tell me where this ladybug is? Why not? Why not?
We don't have it.
What can you tell me? So 3 feet per minute, so over this period of 2 minutes, I can tell you it traveled 6 feet, but do I know the actual location of this bug? No. What information would you need in order to ask that question? What? Right? I would need to know, where did this ladybug start, right? Because you can tell me, well, it's 6 feet from where it started. Okay, but where is it? Well, I don't know, because I don't know where it started, right? Does that make sense? Yes? Okay, so we're developing this concept of this integral, like we're accumulating change, right? So like right here, the area of that curve related to the amount of change, yes? All right, so we can answer this question. Y'all told me 12 feet. We didn't need calculus to answer that question. You answered this question. You told me it was moving 3 feet per minute because it said it was constant, but you cannot answer this question unless we had an initial value. All you can tell me is the change that takes place. All right, so if everything changed at a constant rate, we would not need calculus. Life would be easy. One year, one of my students used that as their senior quote, like in the yearbook. If everything changed at a constant rate, life would be easy, no need for calculus, okay? Like Cameron was able to answer this question, okay, very, very quickly, and he didn't need calculus, right? Okay, but we know, when you get in your car, are you always driving at a constant rate? No. Okay. So let's look at this situation where we have an object that moves along a straight line, and we have 5 snapshots of the velocity. Okay? So over the span of 18 seconds, because on the interval 3 to 21, okay, which is a delta t of 18, object's velocity never decreases. So I can tell you that's always positive. So let's say we want to estimate the distance traveled in the 18 seconds using a right Riemann sum. So when you see that word Riemann on the AP exam, what are you going to think? Rectangle. How do we find the area of rectangle? Okay, length times width, base times height, whatever your preference is. And remember, we're not going to take the time to draw a nice fancy graph. We don't need it. But if I were to draw a graph, I would have velocity on the vertical axis, velocity on the y-axis, and our time on the x-axis. So for a rectangle, the base of that rectangle would not actually be a time value. It would be some delta t, yes? But then the height of this rectangle would be an actual velocity value, right? So just remember that base, it's not going to be one of these 5 time values. It's going to be some delta t, because we're accumulating what happens over an interval of time. All right, so this first rectangle on the interval t equals 3 to t equals 8, what would be our base? 5? 5 what? Good. So distance traveled, approximately 5 seconds. Oops, 5 seconds. And what would be the height of that rectangle? 6 feet per second. So we're using a right Riemann sum. So here's my rectangle, okay, on this interval 3 to 5. And I want to grab the function value, the velocity value on the right side. So 6 feet per second. All right, moving on. The second subinterval from t equals 8 to t equals 11. What would 3 seconds? Our base would be 3. 3 seconds. What would be the height? 9 feet per second. Moving on. Our third subinterval, what would be the base of 6 seconds? And the height? 11 feet per second. And our fourth rectangle, 4 seconds times 18 feet per second. Everybody okay there? Okay. Now, the reason why I can say that this is distance traveled, or let me back up. Do you understand the difference? And you're allowed to say no. If I ask you a question you don't know the answer, it's okay if you say no. Do you know the difference between displacement and distance traveled? Yes? Can you explain it to me? Okay. Say that again. I didn't hear you. Displacement. Okay. So let's say I'm standing here. And let's say I walk 5. I'll just use it. My units are steps. 5 steps to the wall and 5 steps back. What was my distance traveled in steps? 10. So my distance traveled in steps would be 10. What would be my displacement? Okay, because my final position is the same as my initial position. So the word displacement, you got to think change in position. Change in position, but they will use that vocabulary on the AP test. Okay, you will see that phrase displacement, so you have to understand. So when we're talking about displacement, does direction matter? Yes, okay, because I went 5 steps to the right and then 5 steps to the left, okay, so that net change, they combine to be 0, yes? But if I say what's my total distance, do you care about the direction? No, okay, so that'll be important later. So because velocity here is always positive, and it tells me in the prompt that it never decreases, so I know that my velocity is always positive, and in that case, distance traveled and displacement would be equal. You okay with that? Because if I just say, hey, if I walk right here and I walk in a positive direction 10 steps, what's my distance traveled? 10. What's my displacement? 10. Okay, so velocity is always positive. Displacement and distance traveled would be the same. Okay, so, and I'm not worried about doing the arithmetic there. All right, so now let's do this algebraically. We're going to draw a continuous velocity function on some interval a to b and illustrate a right Riemann sum within equal width subintervals. All right, so draw your function. I don't care what it looks like. And we want to accumulate the area from some value a to some value b. And I want to use equal width subintervals. So if I'm using equal width subintervals, what would be the width of each interval? How could I find the width of each interval? I would make subintervals, and what would be the width of those subintervals? Hold on. So real quickly, don't draw this, but if I say, hey, I'm accumulating the area from 3 to 18, and I want to do this in 5 pieces. I want to do this with 5 rectangles. What would be the base of each rectangle? How'd you do that? Where'd you get 15? Okay, so you did 18 minus 3. So in other words, b minus a, and divide it by the number of intervals, the number of rectangles. So the width would be b minus a, which would be the width of the entire interval, divided by n, which is the number of rectangles, the number of subintervals. Now remember, because this is a velocity function, we have time on our x-axis, so this width would be some delta t. So we're going to call this delta t, b minus a over n. Okay? All right, so we're going to start at x equals, or t equals a. We're going to move over that distance that we call delta t. So where would we be on the x-axis at this point? We start at a, and we move to the right delta t. Where am I at now? A plus delta t. And the height of that rectangle would be the velocity evaluated. If I'm using a right Riemann sum, the velocity evaluated at that value a plus delta t. So our first rectangle would have a height, velocity evaluated at a plus delta t times v base, which is delta t. All right, so our next rectangle, we're going to move along the x-axis that same delta t. So where are we at now? We started at a, we move to the right delta t, we move to the right another delta t. Where does that put us? A plus 2 delta t. And I need the height. I'm going to grab the height from the right side. So we're going to evaluate the function at this x time value on the right. So how do I find the height? How would I find the velocity at this value? Just make that substitution. So the velocity evaluated a plus 2 delta t. So there's the height of it. Well, times what? We're just finding the area of this rectangle here. So what's the base of that rectangle? That same delta t. Okay, let's draw one more. So then we're going to go over another delta t. So where are we at now on this time axis? A plus 3 delta t. We're going to grab the height from the right side. So that would be the velocity evaluated at a plus 3 delta t. That would be the height of that rectangle. And what's the base? Times delta t. And without drawing it, what would be the area? How could I find the area of that fourth rectangle? There you go. The only thing that changes would be my velocity value. I would then evaluate it at a plus 4 delta t, but we're using equal width subintervals, so the base of each rectangle is delta t. Everybody okay? All right, so here it is right here. So this is your area of that first rectangle plus the area of rectangle 2 plus the area of rectangle 3, dot, 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 all the way till rectangle n. Now, what does that area represent in this context? So the approximated distance traveled, right? Just like up here, we could relate that distance traveled to area under that velocity curve, right? Distance equals rate times time. Here, we used rectangles to approximate distance traveled. So now, I'm using distance traveled because this area is always positive, right? But we're going to refer to it as displacement. In words, what is displacement? Change in position. Change in position. All right, so this is the approximate change in position. Why is it an approximation? If I think about the area of these rectangles. All right, so I can see that it's not the exact area under the curve because I was using a finite number of rectangles. How many rectangles would we need to get the exact area? An infinite, right? There is no number, there's no magic number, 100, 1,000. There's never enough, right? I need an infinite number of rectangles. And how do we do that? By taking a limit, right? So we're going to accumulate. This is everybody's okay with this summation notation? Okay, did you already make the connection between this Riemann sum notation to a definite integral? Yes? Okay. So we're just summing these up. Rather than this is the expanded form, but if I have 100 rectangles, I don't want to have to write this out. So this is the notation for a summation. This index on the bottom tells you where you start. This tells you where you stop. So like I said, we need an infinite number of rectangles, so we're going to take a limit as n goes to infinity. All right. Are we still okay? All right, so this is an approximation, right? Because without a limit, n is some finite value. Okay, so if we take a finite number of rectangles, we're going to get the approximated change in position. But as soon as I put it through that limiting process, are we okay that this is the actual change in position? Okay, so once we put it through the limiting process, we've taken our approximation and made it exact. All right, so position, velocity, acceleration. Position, velocity, acceleration, PVA. So if we say, hey, our position function, we're going to call it some S of t. Another way we can find change in position, so change in position, final position minus initial, yes? So if I want to know what was the change in position over the time interval a to b, well, I would just find, all right, where's the particle at time b? Where was the particle at time a? Find the difference. So are you okay understanding that these two expressions are equal to each other because they both represent change in position? So basically we are just making the statement that change in position is equal to change in position. Exactly, okay? Both of these expressions, this is two different ways to write the same thing. This expression will give you change in position. This expression will give you change in position, given that we know S of t is some position function. Are we okay? All right. So this equation is the same thing, except rather than using a plus n delta t, we're just calling that some t sub k. where t sub k is some time value in the kth interval. So just a repeat from the last page. This is change in position. This is also change in position. Good? And like I said, position, velocity, acceleration. So position sum s of t. And what's the relationship between position and velocity? Okay, so velocity is the rate of change of position. So I can write velocity as s prime of t. So all we're doing here is I'm rewriting this equation by making substitutions. All right, so we figured out by summing up an infinite number of rectangles where our function value was velocity. We got change in position equal to change in position. Now, this is where you made the connection between this Riemann sum notation into your definite integral notation. Yes? So is everybody okay with this being equivalent to this? I always feel sorry for people who are watching this video and I'm saying this and this and this and you have no idea what this is. Okay, good? All right. So basically, I'm done with this. Okay, so I'm looking here. So when we integrate velocity, we get change in position, which means this right here has to represent change in position. And we just said that velocity is the rate of change of position. So can I make another substitution? Right here. So look right here. We know that velocity is equal to the rate of change of position. So is everybody okay with this expression being the same as this expression? Yes? So guys, that brings us here. So we took this right here, saying, hey, if I integrate velocity with respect to time from A to B, I get change in position from A to B. Velocity is the rate of change of position, which tells me if I integrate the rate of change of position, we get change in position. Good? So I'm going to skip this part right here. So what I'm trying to do is reinforce that a definite integral is the accumulation of change. I always tell people when they ask me, what's calculus? It's a study of motion and change. Derivatives is all about rates of change. Integration is all about the accumulation of change. So when you integrate the rate of change of position, you get change in position. Good? Which is why you couldn't tell me where that ladybug was. With that ladybug example, all you could tell me was the change that takes place. You can accumulate the change that takes place, right? But you can't tell me the actual position without knowing the initial. All right, so if I change this strictly algebraically, so I used a context that you were familiar with, right? This is velocity, rate times time, change in position. But I can change that to any context, any function. So f prime, f double prime. So f prime of t, you got to remind yourself. So when I read this, in my head, I'm not saying f prime, I'm saying rate of change of f. So I say when I integrate the rate of change of f, what do we get? Change in f. So just like with any equation, I can solve for any one of any value. So this right here, change in position. Sorry. We're not dealing with that context anymore. This right here would be the change in position, yes? This value by itself would just be our final position. This value S of A by itself would be initial. So change in position, final minus initial. So I can rewrite this equation. If I wanted to solve this equation for f of b, what would we do? just add f of a. So final is equal to initial plus change. Or I could solve for this variable. Okay, I could add it to the other side and subtract the change. So I read this one as initial value is final minus change. So it's all about change. All right, so this is the big idea. Oh, I forgot, I don't have those other ones typed up on here. Now, if you were to look up, if you were to Google fundamental theorem, let's say you didn't understand the lesson and you're like, I need to go read more about fundamental theorem, you might see this. Integral a to b f of b minus f of a. So the common notation, have you already talked about that? I'm losing my mind. Miss Finnan's not going to invite me back next week. Okay. Okay, so last semester we took derivatives, right? We started with f, we took a derivative f prime, took a second derivative f double prime. And now we're integrating, right? We're starting with some derivative and finding the function. So guys, the antiderivative, the notation, the antiderivative of little f, we call big F. And guys, the College Board is really strict about notation. So if they give you a function and it's named like little a of x, this happened last year. They gave us a function, it was called a, but it was a lowercase a. And students that wrote it with a capital A didn't count, okay? So if you're one of those that likes to write in all caps, okay, be careful. All right, so one step above little f is big F. That's just the common notation, which means little f, when I read this, little f is the rate of change of big F. It's the derivative of big F. You good? So that means if I integrate Are you confused? Okay. So guys, I'm integrating. I'm starting at little f, and I'm going one step up. So this would be written as big F of x minus big F of a. I am losing my mind, Miss Finnan. Please don't save this video. I have convincing evidence that I cannot function with 5 hours of sleep. All right, so I read this as the rate, little f is the rate of change of big F. It's the derivative of big F. So if I integrate rate of change of big F, I get change in big F. Another thing I can do is, what about this right here? I don't care, xt, doesn't matter. What would this yield? Yeah, I'm so glad you were able to answer that question. Or I would feel like a complete failure. Okay, so this is the rate of change of f prime, right? F double prime is the derivative of f prime. In other words, the rate of change of f prime. So if I integrate f double prime from a to b, we get f prime of b minus f prime of a. Good? All right, so now let's put this to work. What is this going to look like? We're going to start with problems that are not contextual, okay? So just remember, this is the accumulation of change. So change is final minus initial. I can rewrite this. Final is initial plus change. Or I can work backwards to find initial. So initial is final minus change, okay? All right, so look at this first example. All right, what are we given a graph of? F prime. And typically on a free response question, they'll tell you at least 3 times what you're looking at a graph of. It'll be labeled, it'll say, hey, the graph of F prime, which by the way is the derivative of F. So just make sure you understand Remind yourself what you're looking at, because College Board likes to give us a graph, but then ask us about something else. Or give us a function and ask us about a different function. All right, so we're looking at f prime, graph of f prime, on this interval -2 to 10, semicircle, and 4 line segments. All right, so all we know about f is that f of 4 is -3. So knowing that f of 4 is -3 and having the graph of f prime, which is the rate of change of f, we want to find these 3 other function values. All right, so how could we find f of 7? So here's what I do. I give myself a little visual. I say, okay, I know the value of f at x equals 4. I'm trying to figure out the value of the graph at x equals 7. So I'm going in a positive direction. So I need to start with what I know, which is f of 4, and add the change that takes place. How do we find change? By integrating rate of change. So we will add the change that takes place from 4 to 7. So we're using this right here. Some final value is initial plus change. Okay? Now, f of 4, that's given, -3. How do I find the value of this? How do I find the value of this definite integral? What? So right now, guys, we're going to use area to evaluate definite integrals. So I'm going to accumulate the area beneath the graph of f prime from 4 to 7. So starting here at 4, I accumulate the change until 7. So what's f of 4? -3 plus. All right, what is this area? So if we can, it's 5, right? Do what? That's what I would do. Yeah. As long as you're accumulating horizontally, I don't like splitting it up like this. But yes, as long as I can accumulate this way, I can see, hey, that's just a square and a triangle. Or you can look at it as a trapezoid. All right, so what's that area from x equals 4 to x equals 7? 5. So what is f of 7? Now, I'm just going to record something here. Here's what I knew. They told me that f of 4 was -3. And we just found that f of 7 is 2. So there is an increase there, right? If f is increasing, it means f prime is positive. So see how f prime was positive over that interval, which is why there was an increase. Okay? All right, what about f of -2? Okay, so, but now I know 2 values on this function, right? I know the value of the function at 7, I know the value of the function at x equals 4, so I can use either one of those, right? I can start at f of 7 and work backwards to 2, -2, or I can start at 4 and go backwards. But either way, we're accumulating, we're going back, right? So this would be f of -2 would be f of 4 minus the change that takes place from -2 to 4. How do we find change? By integrating rate of change. And then we're going to use area to evaluate that definite integral. So we've got f of 4, which was -3, minus. So now we're looking at this area from -2 to +4. So what do we get when we accumulate this area? So what's the area of this semicircle? 2 pi, because the radius of the circle is 2. If I was finding the area of the entire circle, pi times the radius squared would be 4 pi. We only have half of it. So do we agree that that's 2 pi? And then what about this triangle? 2? 2 times 2 is 4, cut it in half because it's a triangle. All right, but you got to be careful to subtract this entire chunk of area. So I need to group it. So -3 take away the quantity 2 pi plus 2. So just for fun, if we want to clean that up, what would that be? -5 minus 2 pi. So now I know the value of this function at -2, and it's -5 minus 2 pi. So from here to here, there was an increase, yes? F was increased on this interval because f prime is positive. All right, you guys find f of 10. So this graph goes to 10, and we're asking for 10. I was looking at the way you set it up. What's the answer on this one? So look at your arithmetic again. Look at your arithmetic again. Oh, okay, look. The base of this rectangle, 1, 2, 3. But this right here is correct. But that is correct. That right there is correct. Okay? But remember, so we're starting at 7, going to 10. So what's the area? How do you find the area of a triangle? Base times height, cut it in half. So 3 times 1 is 3, divided by 2, 3 halves. But because that area is below the x-axis, it's negative. All right, so guys, f of 10. I'm really impressed that most of y'all started at 7. That was good. So we're going to start with something we know, f of 7. So if I start with f of 7, I'm going to have to add the change that takes place. Yeah, there's 3 ways we can do it. And I'm just glad a lot of y'all use that value. So f of 10 plus the change that takes place from 7 to 10. How do we find change? By integrating rate of change. All right, so what was f of 7? We found that in part A. That was 2 plus, what is the value of this definite integral? Negative 3/2. Why is it negative? So the area of this triangle is positive, right? When we talk about area, if I say, hey, what's the area of that triangle? The area of that triangle is 3/2, yes? But because that area is below the x-axis, my f prime values do what? Oh my gosh. What the heck? Was anybody else just wondering what the heck was going on? Y'all were just afraid to say something? All right. So that right there, from 7 to 10, we would be adding a negative 3/2. So 2 is the same thing as 4/2. Take away 3/2. Final answer, 1/2. What's another way we could have done that same question? Okay. So I could have started at 4, right? F of 4, and accumulate all the change from 4 to 10. Or we could have started at negative 2 and accumulate the change from negative 2 to 10. Everybody okay? What time is this class over? Y'all have calculators?
Yes.
No? Okay. Let's just set these up. Let's just set these up, guys. All right, so g prime, rate of change of g, is given by this function. So guys, this would be a calculator question. Please understand, you would not have to do something like this by hand. So this would be a calculator active question. So they give us g prime. They give us one value of the graph of g, and we're looking for 2 additional values. So using what's given, how would we find g of 8? G of 3? What? Okay, hold on. So yes, plus. We're going from 3. No, we know 3. We're trying to get to 8, so we're going to add the change that takes place. How do I find change? By integrating rate of change. So g prime. Let me get this right. So we're accumulating the change that takes place from 3 to 8. Okay, real quick. See this function here? Kind of messy. They've named it for us. If they name a function for you, you can refer to it by its name. Okay? You refer to it by its name. So they've already called it g prime. When I write this expression, I am calling it g prime because 2 reasons. Let's say I try to copy it down, I make a copy error. So then it's wrong, right? I lost a point. And then if I type it into the calculator, but type it in correctly, and I put it equal to the correct answer, now I have an additional problem, which is a misuse of equality. Does that make sense? So that's something that the chief reader emphasizes every year. Tell your students to refer to the functions by their name.